So I had this explain this, and there's A, B, and C. And I'd like you guys to take a minute. You can work with a partner, and I just want to give people just a minute. Can you come back to me in a minute with an answer to A? How are projectiles the beginning of the understanding of orbits? Take a look at the picture. How is this like understanding an orbit? Anybody got anything for me? Come on, we got a nice little cartoon here. You can whisper the answer. I won't even give you a hard time if I disagree. I'm dying here. Save me. All right, I'll do the first one with you. Consider helping me on the next one. All right, so we have a projectile. Projectile fired, but it doesn't have enough speed. Oops, not though. Doesn't have enough speed to miss the Earth. If I say a little statement like that, that doesn't sound very sciencey, but can you see what I mean by that? Especially in the context of the next picture. Maybe you guys, now we have a little bit of language. Can somebody help me out with the next picture? What happens when a projectile is shot so fast that it does miss the Earth? So what we have here is a progression of faster and faster and faster cannon shots. Shot from what looks like the top of a tall mountain if this is the Earth. What's going to happen? What would you say? Yeah, it's going to go into orbit. This is what orbit is, right? In fact, if I were to continue these arrows, these pathways, you guys see that that orbit would shoot the arrow or shoot the cannon right in the back. It would come right back around to where it started from. There's some symmetry to this, right? That's what an orbit is. The path comes back to where it started. And I know these cartoons are simple, but it tells a pretty decent story. Now, if I can think of orbits kind of like projectiles, it also stands to reason that conservation of energy must be a thing. Look at this. If I fire this thing, it has a lot of kinetic energy. Notice the picture's been turned upside down now. We're going to fire it from down here with lots of kinetic energy. So the KE is a big value. That means it's going to have lots and lots of speed here. As it falls towards the Earth, but misses, see how the kinetic energy is going to slow down or it's going to diminish? And when it gets way out here, look, isn't this kind of like somebody threw a ball up in the air above the Earth almost? When it gets up to its highest height, its kinetic energy is minimized, and then it falls back down towards the Earth again. And you notice that there's almost like this anti-symmetry thing on either side of that what's really an ellipse, on either side of that ellipse. And at the top, we have the minimized energy, just like in projectile motion. What we don't usually have in projectile motion is a ball missing the Earth. And so we don't have like maximum speed under the Earth. But boy, if you follow the news and you look at comets or um, interstellar objects or whatever that go through our planets, or sorry, our star system, comets especially, like a comet that's going to come back again, like Halley's Comet, like every 80 years or whatever it is, when it goes past the Earth, it zooms past the sun, I should say, because that's the central body in that orbital system. It goes past at a really high speed when it's nearest the sun. But then when it goes out to the farthest reaches the Kuiper belt, way out there, far beyond the planets, it slows down as it goes out there. And it really does follow this kind of a pattern. And it really is very much like a projectile. So if I was going to add information onto this picture, I really just took this picture here and I blanked it out a little bit. What we're talking about is having lots of EK down here, big EK plus little EG. Up here, we're talking about having a little bit of EK and a lot of EG. And it really is just a trade-off, like when we're on a roller coaster. And it's weird to think that orbital mechanics has some similarities to roller coasters, but it really does. Roller coasters and throwing baseballs, you know? And then somewhere in between, we've got that medium kinetic energy, that medium gravitational potential energy. You know, sometimes I say in grade 11 that it's almost like the total energy is how much money I have in the, I should make this E really big, right? Because this is the sum of both. The total energy is how much money I have in the bank, and the total energy never changes. But if I have a savings account and a checking account, all I'm doing is shuffling around how much money is in each account. It's a conservation of energy thing, okay? Same as roller coasters. Now, if I was thinking about what was happening at D, can you believe that there would be a tangential velocity there, right? So at any moment as I go around this ellipse, there's tangential velocities happening. I just cherry-picked out some critical points, nearest to the central body, farthest from the central body, and sort of in between. And there are actually orbital mechanical names for that. We're going to leave that off to the side for now. There's also an orbital mechanical name for this. There's this thing called eccentricity. And you can imagine in this orbit, sure, the kinetic energy gets to be less at this point, but can you imagine if you're in a situation where the orbit was perfectly circular? Here's my central body. Here's the orbiting body. What would be true about the kinetic energy at all points? Same, right? At all points, we could say that EK plus EG, EK plus EG, you know, based on my way of coding things with the size of the letter. See how the letters are all the same size? Science, right? But if we do this, where it's more stretched out, kind of like this guy here, then we get small EK, big EG, big EK, small EG. And if I go even more extreme, and this is actually, even this isn't as extreme as what an actual comet is like. Like that, right? Like really out there. The EK out here becomes like a dot, and the EG becomes quite dominant. Down here, the EK becomes a heck of a thing, and the EG comparatively is quite small. Now, as I go from this one to this one to this one, there's even a name for that. That's called increasing eccentricity. And when I use the word eccentricity, oh my goodness, my spell check is off. Eccentricity, like electricity. This increasing eccentricity means that this lopsidedness to the EK and the EG at the extreme points is going to get more pronounced. Now, where does the word eccentric or eccentricity come from? Same place as the root word eccentric. And when we think about humans, I have some friends, I have some family that I might consider to be a little eccentric. Somebody who's eccentric is considered to be, it's a little old-fashioned to say it, but they're a little out there, And if somebody's a little out there, eccentric, that's how we use it in English language. A really eccentric orbit means that it goes really out there. That's all. So we should understand what eccentricity means. and that the further out there the thing is going to go, the more lopsided it's going to be, the more imbalanced the orbit's going to be. That's an increase in eccentricity. Okay. So I'll leave it there. Oh, here's another thing before I go away from this page. And I know that there's like some interesting historical facts here, but I'm going to leave that for now. And if you do want to go through and look at the historical facts, this is just for people that are really into the Flat Earth Society. This is something that's been kicking around for around 2,200 years. People were able to use the geometry illustrated in this picture and some basic measurements about light reflecting off the bottom of wells and shadows being projected by vertically standing objects to not only prove that the Earth was round, but to calculate the Earth's radius. And it doesn't take much more than circular geometry understanding and trigonometry to do that proof. And there's some information in this text box if you care to do the proof. And I do not care to have any comments from the Flat Earth Society about this, but you can do the math yourself, okay? And if you want to go find some wells and repeat it, because it's been repeated many, many times, you can do that, despite what all the YouTube videos say, all right? Also, there's no ice wall around the world. Sorry, I've said too much. The Illuminati is coming. So this thing about things speeding up and slowing down. Look here. At this point in the orbit, isn't the orbiting body going to be going slow? At this point here, it's going to be going slow. At this point here, oh my goodness, it's going fast, fast. So there's this fellow Kepler a few years ago. Kepler was really into orbital mechanics. And what he noticed, one of his rules was, hey, since this guy's slower, I bet you it sweeps out. If I let it orbit for 24 hours, like, Earth orbiting around the sun, and I just watched for 24 hours, it would sweep out an area, right? So let's just pretend that delta T here is 24 hours. What Kepler figured out, which is really amazing, because this is honestly like time before computers, right? Like this is freaking cool that he did it with paper and geometry. In 24 hours, see this area that's been swept out? Almost like there was like a second hand on a clock that went tick, 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 tick. The area that got swept out is equal to the area that got swept out if we take a snapshot between point B and point A that's also 24 hours. In other words, what Kepler says is the amount of area swept out by an orbiting body, if I connect the line from the central body to the orbiting body, is going to be equal in area for equal time intervals. And that's related to the speeding up and slowing down of the orbiting body. That's a wild idea. And to have figured it out in an era before computers and AI, I think that's truly impressive. So I'm just kind of like shouting him out for that. Like, yay, Kepler. And if you get a chance to go to Prague and go to Prague Castle and see Kepler's observatory, like, oh my gosh, really great experience. You should do that. Well, let's keep on going.